Okay. Yeah. Good. Good afternoon, everyone. Can you hear me? Yes. Anyone, please confirm.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. We
Okay.
can.
Okay. Fine. Okay. Fine. Okay. So I've already discussed this with Naveen at the start. Okay. Because in the in case I will share my screen also. Okay. We are going to solve the problems on module 1.4, that is unsteady state heat transfer. Okay. So I will share my screen. Okay, so in case if my audio and if you are not receiving the proper audio and video quality from my side, okay, so please interrupt me immediately. Please unmute yourself and please inform me immediately. Okay, that you are not getting proper audio and video quality. Okay, then only I can take some measure. है ना? Then only a corrective measure can be taken. Okay, otherwise in the online mode it is difficult to understand whether you are getting the proper audio and video quality. Is it okay? Fine, fine. Okay, so let's go ahead. Okay, so I'm going to share my screen. Yes, I can. Can you see my screen? Anyone, please confirm.
Yes, sir.
Okay, fine, fine. Okay, so today we are going to solve the problems on module 1.4, that is unsteady state heat transfer. Okay, the problem set I've already sent to all of you well in advance. Okay, before the start of this module. Okay, so you have this problem set. Okay, now let's see, the problem set is on your screen. Okay, so let's solve the problems. So the problem one is, you just read the problem. Problem one is an aluminum alloy plate of 400 mm by 400 mm by 400 mm size at 200 degrees Celsius is suddenly quenched into liquid oxygen at minus 183 degrees Celsius. So starting from the fundamentals or deriving the necessary expression, determine the time required for the plate to reach a temperature of minus 70 degrees Celsius. Okay. So assume the convectivity transfer coefficient equal to 20,000 kilojoule per meter square R degree Celsius, and Cp value is also given, it is 0.8 kilojoule per kg degree Celsius, and the rho, that is density, is also given, that is 3000 kg per meter cube. Okay, now we have to solve this problem. Okay, so we have to determine the time required for the plate to reach the a temperature of minus 70 degrees Celsius. Okay, so this is a problem based on unsteady state heat transfer. Okay, so let's solve this. Okay, so unsteady state. Okay, so let's solve the problem. This is the first one. So first of all, we have to see. Okay, this is problem one. Just a minute. This is the problem one. Okay. Now the dimensions we have to see. So first of all, we have to calculate characteristic length. Okay, or characteristic dimension, and it is nothing but the characteristic length is nothing but volume per unit surface area. Okay, so surface area we have to calculate. Okay, since it is a plate. Okay, what is the dimension? Let's see the dimension. It is 400 mm by 400 mm by 4 mm. Okay, so the length, so you can see if I calculate the surface area, so surface area will be 400 mm by 400 mm, and two sides of plates are there, so that's why we'll multiply this by 2 in order to take the surface area of both the side of plate. Okay, so let's calculate. So it is nothing but uh, 400 mm, so it is 0.4 meters into 0.4 meters. Okay, so this is the surface area and we have to consider both the side of the plate, so we'll multiply it by 2. Okay, so just calculate this. So the calculated value you will get as 0.32 meter square. Okay, so all of you are requested to solve the problems along with me. Okay, so the notebook, pen and the calculator should be there. Okay, so you solve the problems along with me in your notebook and okay, and solve it completely with the help of calculator. Okay, now let's calculate the volume. So volume of the plate will be equal to, it is 0.4 into 0.4 for, okay, 400 mm by 400 mm by 4 mm, so it will be equal to 0.004. Okay, this is the volume. So the calculated value of volume is 0.00064 meter cube. Okay, now we have to calculate characteristic length. So characteristic length is nothing but the volume per unit surface area. So volume we have already calculated is 0.00064 divided by surface area, that is 0.32. Now let's calculate. So the calculated value of characteristic length is 0.002. Okay, now always remember, for solving the problem on the unsteady state heat transfer, okay, first of all we have to check whether the lumped parameter analysis is applicable or Hassler chart is applicable. Okay, so what is the criteria for this? We will calculate Biot number. Okay, Biot number is this. So Biot number, the formula for calculating Biot number is HLC by K. The value of convective heat transfer coefficient is given as 20,000 in the problem. Okay, and the LC value, that is characteristic length, this we have already calculated. It is 0.002. 0.002 divided by thermal conductivity. So what about thermal conductivity? Let's see this. Okay, fine. So definitely in the problem itself, I have not mentioned the value of thermal conductivity. Okay, so fine. So definitely this value of thermal conductivity. Okay, so the some table will be provided to you. If okay, otherwise the thermal conductivity value will be given in the problem itself. Okay, so I've not mentioned the value of thermal conductivity in the problem to understand this. Okay, so you will think about it. How can we get the value of the parameters that are required to calculate the numbers or for solving the problem. Okay, so in the problem I have not mentioned the value of thermal conductivity. So but definitely this value of thermal conductivity will be either given in the problem itself or some table will be provided to you. So with the help of that table you can find the value of thermal conductivity. Okay, so the thermal conductivity value is given as 770. 770.4. Okay, now let's calculate this. So the calculated value of the Biot number will be 0.0519. Okay, so you can see this is the calculated value of Biot number, which is less than 0.1. Okay, this value is less than 0.1, so the lumped parameter analysis is applicable. Okay, so always remember the first step to solve the problem on unsteady state heat transfer is to calculate Biot number. In most of the books, it is okay. In most of the books, at many places they have not calculated Biot number. They have directly used the method, either lumped parameter analysis method or the Hassler chart. But that is not the correct approach to solve the problem. Always remember the first step to solve the problem on unsteady state heat transfer is to calculate Biot number. Fine. So we know if Biot number is less than 0.1, then the lumped parameter analysis is applicable, and if the Biot number is greater than 0.1, then the Hassler chart is applicable. Fine. So now here the lumped parameter analysis is applicable. So just we'll apply the mathematical expression for calculating uh, the required parameter. So the formula is for the lumped parameter analysis T minus TA divided by Ti minus Ta. Okay. And it is equal to e to the power minus HAS divided by rho Vc multiplied by tau in the numerator, and it is equal to e to the power minus Biot number into Fourier's number. So either you use this expression e to the power minus HAS divided by rho Vc multiplied by tau in numerator, or you use this expression e to the power minus Biot number into Fourier's number. Okay, so I am going to use this expression. Okay, the first one. So let's see. Okay, I'm going to use the first one. Okay, this one. Clear? Now that's it. So let's go ahead. So what is the T here? We have to identify that what is T, what is TA, what is TI. Let's see. The aluminium alloy plate, this is the dimension size at 200 degrees Celsius. Okay, so at 200 degrees Celsius, that means it is the initial temperature of this plate. That means Ti is 200 degrees Celsius, right? Now is suddenly quenched into liquid oxygen at minus 183 degrees Celsius. That means in the atmosphere, liquid oxygen is available, and that is maintained at minus 183 degrees Celsius. That means the ambient temperature, that is Ta, is minus 183 degrees Celsius, right? Now determine the time required for the plate to reach a temperature of minus 70 degrees Celsius. Okay, to reach a temperature of this, that means T value is this minus 70 degrees Celsius. Fine. So we have T, Ti, and Ta. Let's put the value. So T is minus 70 minus Ta okay, Ta is minus 183 divided by Ti is 200 minus Ta is minus 183, and it is equal to e to the power minus the value of H is 20,000. Okay. The surface area value we have already calculated at the start, it is 0.32 divided by the value of density is given in the problem itself. It is 3000 kg per meter cube. Now the volume we have already calculated at the start. You can see here we have calculated the surface area. Okay, the surface area, the volume, everything we have calculated. So just put the value 0.00064. The specific heat, let's see what is the specific heat value. Specific heat is 0.8 kilojoule per kg degree Celsius. Okay. So okay, so here we'll put the value of Cp. Okay. Now the only unknown is tau. That's it. And tau is what? The time that we have to calculate. Just calculate this equation. So we have one equation and only one unknown, that is tau. That is nothing but the time. Okay. So here just make this calculation. So you will get it is 0.295. It is equal to, just calculate it. So it is equal to e to the power minus 4166.67 tau. You just take the anti-log, so we can calculate the value of time. Okay, so just calculate this. So the calculated value of time is 1.054 seconds. Okay, so this is the answer. Okay, you just take the anti-log, you can calculate tau, so you will get the value in hours. Okay, you just check the unit. Okay, so the tau value, that is the time value, will calculate in hours, and then in order to convert this into you can just convert the time value from hours to seconds, right? So final answer is 1.054 seconds. Okay, so this is the first problem, right? Now let's go to the second one. Second problem, let's solve. Understood? Anyone please confirm? Hello? Can you hear me?
Sorry.
Yes, sir,
Uh,
we can.
Understood, na? Okay, fine.
Sir.
Okay, in case of any problem, na, in case of any query, okay, so please interrupt me, okay? You unmute yourself and please ask your query. Okay, and you can ask your query in between also, right? Or after the, na? So that will be better. If you ask the query immediately, so that will be better. Okay, and in case if there is some technical issue, maybe audio video quality issue, so you also, yeah, okay, so you all inform me immediately. Okay, so let's go ahead. So let's solve the problem number 2. चलिए अभी problem 2 solve करेंगे. Okay, so question 2 is, just read the problem. A solid copper sphere of 10 centimeter diameter, the density value is given. Okay, so density is this 8954 kg per meter cube. CP value is given as 383 joule per kg Kelvin. Thermal conductivity is given 386 watt per meter Kelvin initially at a uniform temperature. Okay, Ti is equal to 250 degrees Celsius. That means this is the initial temperature, right? Is suddenly immersed in a well stirred fluid which is maintained at a uniform temperature. Okay, Ta is equal to 50 degrees Celsius. Okay, so it is immersed in a well-stirred fluid. Okay, so in the environment, the fluid is available, which is maintained at a uniform temperature, 50 degrees Celsius. That means the ambient temperature is 50 degrees Celsius. The heat transfer coefficient between the sphere and the fluid is 200 watt per meter square Kelvin. That means the convectivity transfer coefficient value is given as 200 watt per meter square Kelvin. Now we have to determine the temperature of the copper block at time 5 minutes after the immersion, right? So again, the problem is based on unsteady state heat transfer. Let's solve this problem. Okay. So, okay, so write down what is given in the problem. Okay, what is given in the problem itself. ओके देखेंगे अभी हम क्या दिया हुआ है प्रॉब्लम में. सबसे पहले तो ये देखिए, जस्ट सी दिस, the copper sphere is having diameter 10 centimeter. 10 centimeter means 0.1 meter. Okay, the density value is given, it is 8954 kg per meter cube. This value is also given. The specific heat value, this is 383 joule per kg Kelvin. This value is also given. The thermal conductivity value, this is given as 386 watt per meter Kelvin. Initial temperature is 250 degrees Celsius. Ambient temperature is 50 degrees Celsius. Convective heat transfer coefficient value is given as 200 watt per meter square Kelvin. Time given, okay. Time given is 5 minutes. You convert this in seconds. So 5 into 60, that is equal to 300 seconds. Fine. Now what we have to determine? We have to determine the temperature of the copper block. Okay, so that means T we need to find. So write down what is to be determined to find. Okay, so we have to find T. Okay, now let's solve this problem. Just solve this. So what is the first step to solve this problem? First step is to calculate Biot number. So Biot number is, the formula for calculating Biot number is HLC by K. Okay, so I need to calculate LC first, characteristic length. It is nothing but volume per unit surface area. So how can I calculate volume? It is a sphere. So the volume of the sphere is 4 by 3 pi r cube divided by the surface area is 4 pi r square. So 4 cancel, this pi cancel, and this r square is cancel. So you will get r by 3. Okay, r by 3. So that means, okay, so yeah, we know the diameter is given as 0.1 meter. Okay, so from this you can find the radius and just put the value. So we can find the value of LC. Calculate the value of LC is 0.0167. 0.0167 meters. Now put the value of LC in the above expression. So HLC by K, H value of H is, you can see the value of H is 200 watt per meter square Kelvin, and thermal conductivity value is this 386. You put the value. So 200 into calculated value of LC is 0.0167 divided by thermal conductivity is 386. You just calculate this. So calculated value of Biot number is 8.64 into 10 to the power minus 3. Okay, so this is the calculated value of Biot number. So the Biot number is less than 0.1. And if it is less than 0.1, that means lumped parameter analysis is applicable. Okay. Now we have to apply lumped parameter analysis. So mathematical expression for calculating lumped parameter analysis is T minus TA divided by Ti minus Ta. It is equal to e to the power minus HAS divided by rho Vc multiplied by tau, and it is equal to e to the power minus Biot number into Fourier's number. Okay, so this is the situation. Okay, so either we can apply this expression or we can apply this expression. Fine, it is up to us. तो लेट्स गो अहेड, चलिए अप्लाई करेंगे। तो T is the unknown, TA. Okay, in the ambient, in the surrounding, what is given? TA is 50 and TI is 250. TA is 50, TI is 250. Okay, and it is equal to E to the power minus HAS. Okay, the value of H is 200, so minus 200 into the calculated value of okay, just we can put all the values. Okay, yeah, okay, I'm providing you a minute. Solve it. Okay, you can you can we can simplify our calculation. Here you can see AS divided by V is there, and we know V by AS, that is volume per unit surface area. It is nothing but LC, and that LC value we have already calculated, right? So we can directly put that value. Okay, no need to put the value of AS and V separately. Fine. So let's do it. So let's do this. Okay. Value of density is 8954. Okay. Now volume per unit surface area. Okay, that value we have already calculated. So 0.0167. We'll put the value here. 0.0167. Now the value of specific heat. Okay, the value of specific heat, what is given? 383. Okay. Now what else? So we have so we have put the value of H rho V by AS. C. Now only thing is we have to put the value of time. Time is 300 seconds. 5 minutes, that is 300 seconds. Okay, this is the equation. So we have one equation and one unknown, that is T. So just solve it so we can find the value of T. Okay, fine. So just calculate this. So the calculated value of T is, okay, you just simplify this. Okay, so finally you will get the value as 0.35. Okay, just simply, okay, just calculate this. So the calculated value of temperature is 120 degrees Celsius. Okay, so this is the answer. Fine. So we have solved problem 2. Okay, so do you have any query in this problem, or can we go ahead?
Right. You can go ahead.
Okay, fine, fine. Thanks. Thanks for the response. Okay. Now let's solve the problem number 3. Read the problem. A thermocouple junction of spherical form. You just see spherical form. Okay, so sphere is there. Okay, we have to make the analysis for a sphere, right? So thermocouple junction of spherical form is to be used to measure the temperature of a gas stream. The H value is given as 400 watt per meter square degree Celsius. Thermal conductivity for the thermocouple junction is given as 20 watt per meter degree Celsius. Specific heat is given as 400 joule per kg degree Celsius, and density is given as 8500 kg per meter cube. Now we have to calculate the two things. First one is we have to calculate junction diameter needed for the thermocouple to have thermal time constant of 1 second. Okay, so that means for the thermal time constant of 1 second we need to find the junction diameter. And second one, we have to determine the time for the thermocouple junction to reach 198 degrees Celsius. Okay, 198 degrees Celsius. If junction is initially at 25 degrees Celsius and is placed in gas stream which is at 200 degrees Celsius. That means here initially at 25 degrees Celsius, that means Ti is this. This is Ti. Okay, this will be, this will be Ti, and is placed in a gas stream temperature of 200. So this will be Ta. Fine. So let's go ahead. So let's solve one by one. Okay, first of all, we'll find this the junction temperature diameter required. Okay, so problem 3 is this. Okay, so problem 3, first of all, write down what is given in the problem. So given is the value of H is given as 400 watt per meter square degree Celsius. Thermal conductivity value is given as कितना दिया है 20. Okay, 20 watt per meter degree Celsius. Now what else? Specific heat. Specific heat is given as 400 joule per kg degree Celsius. Value of density is 8500 kg per meter cube. All these values are given. Now we have to find what is to be determined. Number one, the junction diameter, and number two, we have to find the time required for the thermocouple junction to reach 198 degrees Celsius. So time we need to find. Okay, so let's solve the problem. Okay, so let's solve. So solution. So let's apply. So we have to the junction diameter required for the thermocouple to have thermal time constant of 1 second. Okay, so what is thermal time constant? So let's apply the formula. The thermal time constant denoted by T star is given by rho Vc divided by HAS. Okay, rho Vc divided by HAS. So just make the or simplification. So rho into volume of a sphere is 4 by 3 pi r cube into specific heat divided by H into surface area is 4 pi r square. So 4 cancel, pi cancel, r square cancel. So just simplify this. Okay, so we are getting rho c, rho rc, na? The r is also there. So rho r c divided by 3h. So we got this expression. And in the problem itself, what is given? It is given as for 1 second time constant. Okay, we need to find junction diameter. Very simple. Just put all the values. So 1 second, 1 second time constant. Okay, it is equal to, it is given as 1. Density value is given as 8500. Radius is okay, radius, that means diameter is we need to find. That okay, so that means it is no unknown. We need to find it. Specific heat is 400 divided by 3 into the H value. It is given as 400. So we have one unknown, one equation and one unknown, that is R. Just solve it. So we can find the value of R. The calculated value of R is 0.353 mm. Now we need to find diameter. So diameter will be equal to 2R. It is equal to 2 into 0.353. So therefore D is equal to 0.706 mm. 0.706 mm. Okay. So this is what? This is a junction diameter. Okay. So junction diameter, calculated value of junction diameter is 0.706 mm. That is required for the thermocouple to have thermal time constant for 1 second. Now let's find the second one, that is the time required for the thermocouple junction to reach 198 degrees Celsius if the junction is initially at 25 degrees Celsius and is placed in a gas stream which is 200 degrees Celsius. That means time okay, so that means what is this? This is T and this is 25 degrees Celsius Ti, and this is gas stream environment at 200 degrees Celsius. That means TA is 200 degrees Celsius. That's it. Okay, so now what is the first step to solve this problem? Again, we first of all will find the Biot number. Biot number is what? Formula for calculating Biot number is HLC by K. Okay, so for a sphere, H value LC is R by 3 for a sphere divided by K. I will put the value. The value of convectivity transfer coefficient is given as 400. The radius value we have already calculated, it is 0.353. Okay, this is the value we have already calculated, is R value 0.353 and the unit is mm. So we have to convert this, the unit of radius, from mm to meters. So multiply by 10 to the power minus 3 divided by 3 into thermal conductivity. Okay, thermal conductivity is 20. So just calculate this. So the calculated value of Biot number is 0.00235. 0.00235. That means Biot number is less than 0.1. So the lumped parameter analysis is applicable. Okay, so lumped parameter analysis is applicable. Now apply the expression for the lumped parameter analysis. So the expression is T minus TA divided by Ti minus Ta is equal to e to the power minus HAS. Put the value e to the power minus HAS divided rho Vc multiplied by tau, and it is equal to e to the power minus Biot number into Fourier's number. So this is the expression. Now just calculate this. So either you use this expression or this expression. We can find a solution. Okay. So I'm going to use the first one. So put the values. We'll put the values. T is what? 198 minus TA is 200 degrees Celsius. You can see we have already marked. T is 198, TA is 200, TI is 25. 198 minus 200 divided by 25 minus 200 is equal to e to the power minus h into 4 pi r square into tau divided by rho into 4 by 3 pi r cube into c. So you can see 4 cancel, pi cancel, r square, and this is also cancelled. Okay. Now you just put all the values. Put all the values. So what are the values? Okay, just solve it and give me the answer. All the values are given. Okay, so just simplify this. So it will be equal to e to the power minus 3h divided by rho rc. Okay, into tau. Minus 3h divided by rho vc into tau. So we got this expression. Now we'll put the values. So this is 198 minus 200 divided by 25 minus 200. It is equal to e to the power minus 3 into h. The value of h is given as, if h is given as 400, divided by rho. The value of rho is 8500. 8500 into r into r. Value of r is 0.353. This is the value of r. 0.353 mm. Okay, we'll do this. So put all the values and find the answer. Specific heat value is 400. Okay, so 3 into 400, that is the value of H divided by rho. Density value, okay, we have already put, and then this R is 0.353 mm. 0.353 mm. So convert this in meters to 0.3 multiplied by specific heat. C, specific heat value is 400. Okay, specific heat value is 400. Okay, multiplied by tau. That's it. So you can see we have one equation, only one unknown, that is tau. So we can find the value of tau. Okay, we have one equation and one unknown, that is tau, that is time. We'll just solve it. Okay, we will get okay, just solve this value. So we'll get this as e to the power some factor, take the anti-log. Okay, so we will be able to find this tau. Okay, so we have one equation, one unknown. We can solve it and we can find. So the answer is 4.47 seconds. 4.47 seconds. Okay. So this is the answer. Okay, fine. So any doubt in this problem? Or can we go ahead?
Go ahead, sir. Go ahead.
Okay, fine. Okay, so let's solve this problem fourth. Just read the problem. A 60 thick large steel plate thermal conductivity is given as 42.6 watt per meter degree Celsius. Alpha is 0.043 meter square per hour. Initially at 440 degrees Celsius, is suddenly exposed on both sides to an environment with convective heat transfer coefficient 235 watt per meter square degree Celsius and temperature 50 degrees Celsius. Now we have to determine the center line temperature and the temperature inside the plate 15 from the mid plane after 4.3 minutes. So this is the problem. So let's solve this problem. Okay, I'm providing you 2 minutes. Okay, just initiate this problem. And then, okay, after this, we will start discussing this problem and we'll solve the problem together. Okay, so you have the problem set. Okay, I'm unsharing this. Okay, we initiate this problem 4. Then I'll see is whether your approach is okay or not. Okay, so I have given you okay few minutes. Just initiate this problem uh, 4, okay, and then we will solve the problem together. Uh, okay, so let's solve. Okay, so can you see my screen? Anyone please confirm?
Yes, sir. Yes, sir.
Okay, fine, fine. Okay, so question number 4. Okay, so let's solve this problem. Question 4. So in the question 4, what is given? A 60 mm thick large steel plate. Okay, so thickness is 60 mm. Okay, so we denote the thickness as 2L. So 2L is 60 mm. So it is equal to 0.06 meters. Fine. Thermal conductivity of this steel plate is given as 42.6. watt per meter degree Celsius. Now, what else? Yes, thermal diffusivity is also given. It is 0.043 meter square per hour. Okay, this value is also given. 0.043 meter square per hour. Now, initial temperature. What about initial temperature? Let's see. Suddenly exposed to both the environment with convective transfer coefficient. H value is given. This is H. Okay, this is H value. And this is the T value. Okay. So, fine. And let's see. Okay, 60 thick large steel plate thermal. These are the values given. Now initially at 450 for 40 degrees Celsius. So that means Ti is this. Okay, 440 degrees Celsius. So 440 degrees Celsius. Now what about H? H is given as 235 watt per meter square degrees Celsius. Two 35 watt per meter square degree Celsius. Now what about Ta? Okay, so let's see. Ta is this. This is exposed on both the side, okay, with the environment with having H value this and temperature this. That means it is exposed to the surrounding, which is having temperature 50 degrees Celsius. That means the ambient temperature is 50 degrees Celsius. So Ta is 50 degrees Celsius. Now what about time? Time is, you can see, 4.3 minutes. 4.3 minutes. Now what we have to determine? This is the question. So we have to find the center line temperature and the temperature inside the plate, 15 from the mid plane. So this we need to find. Okay. The first step for solving the problem is to calculate Biot number. So calculate it. Calculate it. Okay. So let's solve. The first is we have to find the center line temperature, and second one we have to find the temperature at temperature inside a plate 15 from the mid plane. Now just solve this problem. Let's solve. Okay. So let's solve the problem. The first step for solving the problem is to calculate Biot number. The formula for calculating Biot number is HLC by K. Okay. Now we have to calculate LC. LC is what? LC is the thickness is 60 So the semi thickness is the characteristic length. That is 60 by 2. That is 30 That means it is equal to 0.03 meters. Now the Fourier's number. Okay, so let's solve this first, and then we'll go ahead later about the other numbers and all. Okay, so let's calculate the Biot number first. Okay. Just calculate this. Biot number first, H value. H value is given as 235. LC, we have already calculated. It's a semi thickness of the plate, that is 0.03, and thermal conductivity is given as 42.6. Okay. So these are the values. Okay, we have put to calculate Biot number. So just calculate the Biot number. So calculated value of Biot number is 0.165. Okay, which is greater than 0.1. So that means the Hessler's chart is applicable. Okay, Hessler chart is applicable. Okay, now let's apply. So we know how to use the Hessler chart. I've already explained this in the class. Just a minute. Just a minute. One minute. Okay, so I will show the Hessler chart. Okay, just give me a minute. How to use it, we have already discussed. Okay, so let's see. This is the Hessler chart. Okay, so since this is a problem on plate, so we will use the Hessler chart. You just see this, the Hessler chart for the temperature history at the center of the plate having thickness 2L. Okay, so this Hessler chart we will use. I've already told you, if we have to find the center line temperature or the temperature at the mid plane, then we have to use the Hessler chart for that particular geometry. Okay, for getting the temperature history at the center line or at the mid plane. Okay, or if we need to find the temperature at the location other than mid plane, then we will use first of all we will use the Hessler chart. So we will find this parameter T naught minus T divided by Ti minus T, and then from with the help of we will with the help of correction factor chart of that particular geometry. That means we will use the correction factor chart of that particular geometry. Here in this problem we have taken the plate, so we will use the correction factor chart of the plate, and then we will multiply the correction factor with this temperature distribution factor. In this way we can find the temperature at the location other than mid plane. Okay, so let's solve this. So we have already I've already explained how what is Hessler chart and how to use the Hessler chart. Okay, so I've already told you four geometries are there: plate, sphere, cylinder, and cube. Okay, plate, cylinder, sphere, and cube. So separate Hessler charts are available for these geometries. Okay, so if we have to find the temperature at location other if we have to find a temperature at the center line or at the mid plane, then we can use the Hessler chart of that particular geometry. And if we have to determine the temperature at the location other than mid plane, then we will use the correction factor chart of that particular geometry. From that correction factor chart, we will find the correction factor, and then we will multiply that correction factor with this parameter, that is the temperature distribution. In this way we can find the temperature at the location other than mid plane. Fine. So here our problem is based on a cylinder. Okay, so we are using the Hessler chart for the sorry, the problem is based on plate. Sorry. Okay, the problem is based on the plate, so we will use the Hessler chart for the plate. Clear? So now we know for the Hessler chart, on the x-axis the Fourier's number is there, and on the y-axis this parameter is there, T naught minus Ta divided by Ti minus Ta. And what about these lines? Okay, these lines are nothing but 1 upon Biot number. Okay, these lines are nothing but these are the uh, 1 upon Biot number. Okay, so first of all we have already calculated Biot numbers. We'll calculate 1 upon Biot number, and then we'll calculate Fourier's number, and on the basis of these two numbers we'll locate a point on the chart, and then we'll take the horizontal projection. This way we can directly find this temperature distribution value. Let's find this. So Biot number we have already calculated. Okay, it is 0.165. So we will calculate 1 upon Biot number first. Let's calculate 1 upon Biot number. So 1 upon Biot number is 1 upon 0.165 is equal to 6.06. Okay, and now we'll find the Fourier's number. So Fourier's number is what? Fourier's number is alpha tau by LC square. Okay, now let's calculate this Fourier's number. Fourier's number is equal to alpha tau by LC square. So alpha value is given as 0.043 meter square per hour. Okay, into you can say 4.3 minutes. Okay, so we will just convert this. Okay, so this is 4.043 meter square per hour. So in the hour we'll convert this into seconds. So 3600 seconds multiplied by 4.3 minutes. So 4.3 minutes. So we have to convert the minute into seconds. So multiplied by 60. Okay. Now divided by LC square. So LC is what? LC is 0.03 meters. This we have already calculated. So 0.03 square. Okay, now I'll just we'll calculate this. So 0 cancel, and this is 6. This is about 60. Okay, so we are getting 0.043 into 4.3 divided by 60 into 0.03 square. Just calculate this. So the calculated value of Fourier's number is 3.424. Okay, now we have the Fourier's number. Okay, therefore Fourier's number is 3.424. Okay, so this is the Fourier's number, and this is 1 upon Biot number 6.06. 6.06 is the 1 upon Biot number, and Fourier's number is 3.424. Okay, now let's use the Hessler's chart. First, okay, so we have calculated by Fourier's number. It is 3.424, and 1 upon Biot number, that is 6.06. 6.06. Okay, so with the help of this 1 upon Biot number and Fourier's number, we will be able to locate a point on this. Okay, and then we will take the horizontal projection. Clear? क्या किया हमने? देखो, Hassler chart में 3 parameters. On the x-axis Fourier's number is there, and on the y-axis this temperature distribution is there, T naught minus T divided by Ti minus Ta. And what about these curves? These curves are expressed in the form of 1 upon Biot number. So what we will do? So we have already calculated Fourier's number. The calculated value of Fourier's number is 3.424. and we have already calculated 1 upon Biot number. The value of 1 upon Biot number is 6.06. So with the help of this Fourier number and 1 upon Biot number, we will locate a point on this chart, and then we will take the horizon. Then we will take the projection. Okay, so from this we can directly get the temperature distribution value directly. Okay, so you just see here in our case, so this is about the mid planes. So x by L will be 0 since x is 0. So this temperature distribution value will directly get. So okay, so we got the value as 0.6 from the Hessler chart directly. Okay, so T naught minus T divided by Ti minus Ta is 0.6. So T naught minus Ta divided by Ti minus Ta, and the value we got is 0.6. We need to find the center line temperature, so we don't know T naught. Ta I know it is 50 and Ti is 440, and it is equal to 0.6. So from this we can directly find the value of T. Sorry, T naught. We can directly find the value of T naught. So T naught is, calculated value of T naught is 284 degrees Celsius. So what is this? This is the center line temperature or the mid plane temperature. Okay, so we have determined this first one. Okay, so any doubt so far? किसी कोई doubt? Or can I go ahead?
Sorry, you can go ahead.
Okay, fine. Okay, now let's calculate the the temperature inside the plate 15 mm from the mid plane. So let's see this. Now after this, we will determine the second one. So second is, first of all, we'll calculate x by L. So first of all, this is the situation of a plate. Okay, so let's try to understand the situation. This plate is having thickness 60 mm. That means 2L is 60 mm. I need to find. Okay, so in the above case, we have already determined the center line temperature or the mid plane temperature. Now, in this case, we need to find the temperature at 15 meter away from the 15 mm away from the mid plane. So this is what this is. This is what this is the 15 mm away from the mid plane. Okay, so you can see here, if thickness is 60 mm, so semi thickness will be equal to, this will be equal to 30 mm, and this is also 30 mm. Okay, this is 30. So semi thickness is 30 mm. Fine. Now we have to calculate x by L. So x by L will be equal to what? Okay, so the semi thickness is 30, and the location is 15 mm away from the mid plane. So minus 15 divided by L is what? L is the semi thickness, that is 30. So it is 15 by 30. It is 1 by 2. It is equal to 0.5. Okay. Now you just see here the correction. Now we will use the correction factor chart for this. So you just see here, I can show we have to use a correction factor chart for the particular geometry. So this is the Hassler position correction factor chart for a plate. So you can see here on the x-axis 1 upon Biot number is there. So this we have already calculated. And what about this? These equations are expressed in terms of x by L, in terms of x by L for the plate. Okay. And these are expressed in terms of small r by capital R in case of cylinders and spheres. Okay. So it is expressed in terms of small r by capital R in case of cylinders and spheres. Okay. So let's here the problem is based on plate. So we have to find a Hassler position correction factor chart for the plate for the temperature history at the location other than mid plane. Okay. So here we will use the Hassler position correction factor chart for temperature history in the plate. So you can see here we have already calculated 1 upon Biot number. 1 upon Biot number is what? This we have already calculated. 1 upon Biot number is 6.06. Okay. So 1 upon Biot number is 6.06 and we have already calculated x by L. So let's see. So you can see this is 1 upon Biot number and these curves are expressed in terms of x by L. So on the basis of this 1 upon Biot number and x by L, we will locate a point on the curve. Okay. We can locate a point on the curve. Suppose this is a point on a curve. And then we will take the horizontal projection. And when we will take the horizontal projection, so we'll directly get the value of t minus ta divided by t naught minus ta from the correction factor chart itself. Okay, so t minus ta divided by t naught minus ta. Okay, so after my marking I got 0.97. So I will write the value t minus ta divided by t naught minus ta. It is equal to 0.97. Okay. So you can see here. So this is t is what? So t we need to find minus ta. Ta is 50 divided by t naught. T naught value we have already calculated. T naught is 284. 284 minus ta. Ta is 50 and it is equal to 0.97. So we have one equation and one unknown, that is t. Solve this equation so we can find the value of t. The calculated value of t is 276.98 degrees Celsius. So this is the answer. Okay, this is the answer. That means this is the temperature at the 15 mm away from the mid plane. Okay, temperature inside the plate 15 mm away from the mid plane. Clear? Suppose if in a particular problem there is no need to find, it is not asked to find the center line temperature. Okay, so what you will do? So you can directly solve the problem. How? You can just use the Hassler chart. From that you can find that this expression t naught minus ta divided by ti minus ta. Let's write this. Okay, this is alternate way, the shortcut. Okay, so I can find T naught minus TA divided by Ti minus Ta. And from the correction factor chart, I can find this correction factor, T minus T divided by T naught minus Ta. T minus Ta divided by T naught minus Ta. So we have multiplied this correction factor with this temperature distribution directly. So this T naught minus T and T naught minus Ta will cancel out. So we'll get the value as T minus Ta divided by Ti minus Ta. So in this way also, we can directly find the value of T, that is the temperature at the location other than midplane or the center line, without determining T naught, that is the midplane or the center line temperature. Otherwise, if it even if it is not asked in the problem to determine center line or the midplane temperature, we will follow the similar procedure. First of all, we'll find the center line or the midplane temperature, and then we will use the Hessler correction factor chart, and from that we will find the correction factor, and then fine, and then we can directly so in that expression, okay, in that correction factor expression, the T naught factor is there, and so we will put, that is that center line or mid plane temperature is there, so we'll put the value of the center line temperature or the mid plane temperature in that expression itself, and then we can directly find the temperature at the location other than mid plane within the geometry. Fine. So this is how we can solve the problem with the help of Hassler's chart. Now let's see. So if suppose if okay, so I've already told you the Hassler charts are available for the different geometries. From the subject point of view, the four geometries are there. That is the plate, cylinder, sphere, and cube. So separate Hassler chart is available for the separate geometry. Okay, this is a Hassler chart. Okay, just see this. This is a Hassler chart for the plate. This is the Hassler chart for the cylinder. This is the Hassler chart for the sphere. Okay, and likewise there is Hassler chart for the cube also. Now you can see this is the correction factor chart for the plate. Okay, correction factor chart for the cylinder, and okay, and this is the correction factor chart for the sphere. Okay, so we can find the okay, so separate correction factor charts are available for the separate geometries. Okay, so we will use the correction factor chart of that particular geometry, for which we have to find the temperature at the location other than midplane, and from and we will find the correction factor from the correction factor chart, and we'll multiply that correction factor with the temperature distribution that we have already determined from the Hassler chart. Okay, else we will find T naught value from the Hassler chart, that is center line or the midplane temperature, and then we'll find the correction factor. So that is this expression, and we will put the value of T naught, that is center line or the midplane temperature, in that expression itself. So in this way, we can directly find the value of T. This is the way for solving the problem. And always remember this for the correction factor chart for the plate, these curves are expressed in terms of x by L, and for the correction factor chart of this cylinder or sphere, these curves are expressed in terms of small r by capital R. Okay, this is for cylinder, so small r by capital R. Okay, so you can see these curves are expressed in terms of x by L for the plate, and these curves are expressed in terms of small r by capital R for the cylinder. Okay, and these curves are expressed in terms of small r by capital R for the spheres also. Okay, for the spheres also. Okay, for the sphere. So in short, I can say these the correction factor chart, the on the x-axis the 1 upon Biot number is the variable, and on the y-axis the correction factor is the variable, that is T minus Ta divided by T naught minus Ta. Okay, where Ta is the ambient temperature and T naught is the center line or the mid plane temperature, and these curves are the curves are there, and these curves are expressed in terms of x by L for the plate. Okay, and these curves are expressed in terms of small r by capital R for the cylinder, and these curves are expressed in terms of small r by capital R for the sphere. Okay, that means these curves are expressed in terms of small r by capital R for the cylinder and sphere. Fine. So this is the way to use the Hassler chart. Is it okay? Is anyone please
Yes, sir.
confirm?
Yes, sir.
Understood, na?
Ah, sir.
Okay, okay, fine, fine. So let's go ahead. Okay, अभी हम problem next problem ले लेंगे. So next problem is the problem 5th. Just solve this problem. It is one of the classical problem, always asked a number of times in the exam. Okay, so just do this. Problem set open करेंगे. The problem set is the problem set on what? This is unsteady state. Okay, so this was the problem set. Okay, so problem 5. Okay, let's solve problem 5. An egg with a mean diameter of 4 centimeter and initially at 25 degrees Celsius is placed in a boiling water pan for 4 minutes and found to be boiled to the consumer's taste. Now, for how long should a similar egg for same consumer be boiled when taken from a refrigerator at 5 degrees Celsius? Use a lumped parameter theory and presume the following properties for the egg: thermal conductivity, convective heat transfer coefficient, specific heat, and the density is given. Fine. In the problem, it is given as lumped parameter analysis to solve the problem by the lumped parameter theory. However, in mostly it will not be mentioned in the problem. We have to calculate Biot number, and then after calculating Biot number, we have to identify whether the lumped parameter analysis is applicable or the Hassler chart is applicable. Right? Now let's solve. Okay, let's solve this problem. चलिए करेंगे. So this okay. So problem 5. Problem 5. Okay, so a minute. Just give me a minute. I want to okay, I just want to open the another file. Just give me a minute. Just a minute. Okay, I have given you a minute. You just try to solve this problem. Okay. So let's see. So the problem 5 is this. An egg with mean diameter of 4 centimeter and initially at 25 degrees Celsius placed in a boiling water pan of for 4 minutes and found to be boiled to the consumer's taste. For how long should a similar egg for same consumer be boiled when taken from a refrigerator at 5 degrees Celsius? Use lumped parameter theory and presume the following properties, right? So let's see. So first of all, the first step is to calculate Biot number. Let's solve. So Biot number is HLC by K. Now how can I calculate by LC? LC is what? Characteristic length. It is volume per unit surface area. So it is egg. Okay, it is a problem based on egg. So egg is what? Egg is a which type of geometry is this? Egg is a sphere. Okay, so we'll apply the formula for the sphere. So volume of a sphere is 4 by 3 pi r cube and surface area of a sphere is 4 pi r square. So 4 cancel, pi cancel, r square cancel. So ultimately we got r by 3. So r is what? R is given as in the problem the diameter is at 4 centimeter. That means radius is 2 centimeter. That means 0.02 meters. It is 0.02 meters divided by 3. So it is equal to 0.000, sorry, 0.00 uh, 666 meters. Okay, 0.00666 meters. So this is a calculated value of characteristic length. Now we'll put the value of characteristic length in the above expression for calculating Biot number. So HLC by KH is 125. Okay, so just a minute. I will calculate this Biot number below. Biot number is HLC by K. So H is what? H is 125. Okay, you can see 125. The calculated value of LC is 0.00666 divided by thermal conductivity. Thermal conductivity is 12 watt per meter degree. Okay. The calculated value of Biot number is 0.0694, which is less than 0.1. That means the lumped parameter analysis is applicable. Okay, now let's solve the problem. Apply this lumped parameter analysis. So T minus TA, the expression for lumped parameter analysis, T minus TA divided by Ti minus Ta. It is nothing but the excess temperature theta at any place divided by theta, that is the excess temperature initially. It is equal to e to the power minus HAS divided by rho Vc multiplied by tau. In the numerator, it is equal to e to the power minus Biot number into Fourier's number. Okay. Now let's apply this expression. Okay, so let's work for this okay, so generally I can find the solution either by using this expression or this expression. So I'm going to use this expression. Okay, and let me simplify this term so it will be easy for making the calculation. So let's see. We will just calculate this term. This is HAS divided by rho VC. We know, let's simplify this. Volume per unit surface area is characteristic length. So I can write like this. This is H divided by rho C LC. Okay, so let's calculate this. H value is 125 divided by the density value is 1250 multiplied by the specific heat value. That is what? What is the specific heat value? Let's see this. It is 2 kilojoule per kg Kelvin. Okay, so 2 kilojoule. Okay, so convert this in joule. So multiply by 1000. So 2 into 1000. So 2 into 1000 multiplied by LC. So calculated value of LC is this. LC is this 0.00666. 0.00666. Okay, so we have determined this. Okay, so we have okay, we are putting all these values in this expression. Okay, so the calculated value is 0.0075. Okay, so this we got this value, and since we are interested in the entire term, in this entire term, okay, so we can say this is multiplied by tau. Okay, so this is I divided by rho C LC into tau. Okay, so it is equal to 0.0075 into, it is 4 minutes. 4 minutes. Okay, just solve this. Solve कर लीजिए. 0.0075 into 4 into 60. So the calculated value is 1.8. Okay, so let's put all these values in this expression. So we can easily solve it. Okay, let's do this. So T minus TA. So T we okay, I have to find minus TA is what? This we have to understand. An egg with mean diameter 4 centimeter initially at 25 degrees Celsius. That means initial temperature Ti is, this is what? This is Ti. Okay, it's placed in a boiling water pan for 4 minutes. Boiling water pan means, that means the boiling water is there and the boiling temperature is what? 100 degrees Celsius. Okay, so the environment, the boiling water is there and the boiling water is having 100 degrees Celsius. So TA will be equal to 100. Okay, so let's put the value. So T minus TA, that is 100 degrees Celsius, divided by Ti, that is 25 minus TA 100. It is equal to e to the power minus this term. Okay, so e to the power minus this term, that is 1.8. ओके, कर लीजिए. ओके, सो है ना, हमने ये जो टर्म था इसको पूरा सिंप्लीफाई करके हमने कैलकुलेशन कर लिया है अलग से. तो हम यहाँ पर वैल्यू हमने पुट कर दिया है 1.8. So now we have one equation and one unknown, that is t. Just solve it so we can find the value of t. So the calculated value of t is 87.6 degrees Celsius. Okay, so this is the answer. Okay, now let's see what is the second thing. So, what we have to find? An egg with mean diameter of 4 centimeter, initial 20 degrees Celsius, is placed in boiling water pan for 4 minutes and is found to be boiled to the consumer taste. For how long should a similar egg for the same consumer be boiled when taken from a refrigerator? Okay, so for how long a similar egg for same consumer will be boiled? That means we need to find time. Okay, हमें यानी कि time find करना है. So let's see. ओके, तो अभी हम सेकंड केस के लिए अप्लाई करेंगे फॉर हाउ लॉन्ग. सो यू कैन सी हियर for how long should a similar egg for same consumer be boiled when taken from a refrigerator at 5 degrees Celsius? That means now TI is this 5 degrees Celsius. This is TI now. Clear? And again, it is there in the surrounding having boiling temperature, that is 100 degrees Celsius. So TA is again 100 degrees Celsius. So let's go ahead. Now let's solve the second part of this question. So you can say the expression is T minus TA divided by Ti minus Ta. It is equal to e to the power minus HAS divided by rho Vc multiplied by tau in the numerator. So what is T? T we have already determined. T is 87.6. So 87.6 minus TA. TA is 100 degrees Celsius divided by Ti. Now Ti is 5 degrees Celsius minus TA, that is 100 degrees Celsius. It is equal to e to the power what? What about this factor? HAS divided by rho Vc. This HAS divided by rho Vc we have already calculated. You can see this. I have already calculated this value. Fine. Let's put the value from there only. So this is what? कितना है इसका वैल्यू? इसका वैल्यू है इसका वैल्यू 0.0075. 0.0075. So minus 0.0075. Okay. Minus 0.0075 tau. Okay. Now just so we have one equation and one unknown, that is tau. So we can find the value of tau. Just take the antilog. So we can find the value of tau. So the calculated value of tau, that is time, is 271.47 seconds. Okay, 271.47 seconds. Okay, the answer is 271.47 seconds. Okay, if you want to convert this in minute, so you know 1 minute is equal to 60 seconds. Okay, the 1 second will be equal to 1 upon 60 minutes. Okay, fine. 1 minute is equal to 60 seconds. So 1 second will be equal to 1 upon 60 minutes. So if we want to calculate this in minutes, so we can convert it in minute. So it is calculated value is 4.524 minute. So this is the answer for this. Yes, understood? समझ में आया कि कोई डाउट है?
Yes, sir. Understood.
हेलो हेलो यस नवीन Understood, na?
Yeah, understood, sir.
Okay, okay, fine, fine. So can I go ahead? Okay, so let's
Yes,
go
sir.
ahead. Question 6. So read the problem. A large steel plate 50 thick is initially at a uniform temperature of 425 degrees Celsius. It is suddenly exposed on both sides to an environment with convective coefficient 285 watt per meter square Kelvin and temperature 65 degrees Celsius. Determine the centerline temperature and the temperature inside the plate. 12.5 from the midplane after 3 minutes. For steel, the thermal conductivity and thermal diffusivity value is given. Okay, we have to solve this. So let's see. This is the problem number 6. Problem 6. So we know the thickness is given as, in this problem, the thickness is given as 50 Okay, so therefore, the semi thickness will be equal to 25 Okay. Now, okay, so you see this. So now we will calculate the Biot number first. So let's calculate Biot number. So the Biot number is HLC by K. So this H is, you just see here, H value, you can see the convective thermal this is 285. Okay, and this TA is 65. You can see this is H. Okay, ये H है, ये आपका क्या है, ये आपका TA है 65. Okay, ये आप this is tau, this is time. Okay, this is initially at a uniform temperature 425 degrees Celsius. This is Ti. Okay, this is thickness, so that is 2L. Okay, this is 2L. Fine. So let's solve. H, value of H is 285 LC. LC क्या होगा? LC is nothing but the semi thickness. This, okay, so that is this one. This is nothing but semi thickness is the characteristic length, so it is 25 So convert this in meters, so multiplied by 10 to the power minus 3 divided by thermal conductivity. Value of thermal conductivity is 42.5. Yes, 42.5. This is given. Now let's calculate Biot number. The calculated value of Biot number is 0.167, which is greater than 0.1. So Hessler's chart is applicable. Okay, clear? Hessler chart is applicable. So I am providing you a minute. You tell me how to. Okay, you use the Hessler chart and try to find a solution. Okay, I'm just providing you 2 minutes. Okay, and then we'll continue. We'll solve the problem together. So by that time, I'm unsharing the screen.
सर हेमल रिमूव हो गया था, उसको मीटिंग में ऐड कर लो। हेलो।
Okay, now let's solve. Okay, so I have again shared the screen. So you just see. Okay, so you can see here, if the biot number here, we got the value of biot number as 0.167, which is greater than 0.1. That means Hassler chart is applicable. And the problem is based on a plate. So we have to use the Hassler chart of a plate. Clear? So we'll go to that. Okay, so just a minute, I will. One minute, please. I want to share that. Okay, so I have identified all these values here, right? Now let's go ahead. I want to open this. One minute, please. Okay, so I will open this book again. No. Okay, so just see this. So you can see here. Now we'll use the Hessler chart for a plate. So you can see this is the Hessler chart. No, this is for the sphere. Okay, this is for a cylinder. Now this is the Hessler chart for the plate having thickness 2L. So we will use this Hessler chart. Okay. We have already determined these curves are expressed in terms of 1 upon Biot number. So Biot number we have already calculated. So we'll calculate 1 upon Biot number and we'll calculate Fourier's number. So let's do this. And then with the after this we will locate the point here on this graph. Okay, so let's solve. We'll calculate. Biot number is calculated, so we'll calculate 1 upon Biot number. So 1 upon Biot number is equal to 1 upon 0.167. So the calculated value is 5.988. Okay, and Fourier's number. How can you calculate Fourier's number? Fourier's number is equal to alpha tau by LC square. What is the value of alpha? So let's see the value of alpha. Alpha value is this 0.043 meter square per hour. Okay, so 0.043 meter square per hour. So we'll convert this in seconds. So 1 hour, 3600 seconds are there. Time is what? Time is 3 minutes. So we will convert just a minute. We'll see what is the time. Time is 3 minutes. So in 1 minute 60 seconds are there. So we will multiply it by 60 divided by LC square. So the calculated value of LC is this 25 mm, the semi thickness. Okay, so 25 mm, we will convert this in meters and square. We will take the square of this. So in this way, we can calculate the Fourier's number. So the calculated value of Fourier's number is 3.44. So we have determined the value of Fourier's number and we have determined the value of 1 upon Biot number. Okay. Now for the mid plane temperature, definitely the x will be 0. And if the x is 0, so x by L will be equal to 0. Okay. So now let's open this. For is number 3.44 and 1 upon Biot number 5.988. So you can see here the Fourier's number. Okay. And this is one, this shows these curves shows this curve shows 1 upon Biot number. Okay, these curves. So fine. So now let's locate the point on this graph. So you can see with the help of Fourier's number, the value of Fourier's number is 3.44 and 1 upon Biot number is 5.988. So with the help of Fourier's number and 1 upon Biot number, we will locate a point on this chart. And then after this, we will take the projection We will take the projection. So we can directly get the value of this T naught minus Ti divided by Ti minus Ta. So we got the value as 0.6. Okay. So let's note down this. So we got the value as T naught minus Ta divided by Ti minus Ta is equal to 0.6. Now we'll put the value. T naught, we need to determine this. Minus Ta is 65 degrees Celsius divided by Ti is 425 degrees Celsius. Ta is 65 degrees Celsius and it is equal to 0.6. So from this we can directly find the value of T naught. That is the center line temperature or mid plane temperature. The calculated value is 281 degrees Celsius. So we got this value. Fine. So what we have to determine the center line temperature. This center line temperature we have determined. The center line temperature we have determined. Now we have to find the temperature inside the plate, 12.5 mm from the mid plane. So let's draw a plate. This is a plate. Just a minute. This is the plate. This is the center line of this plate. Just give me a minute. Okay, so this is the center lines of this plate. So the thickness of this plate is 2L, that is equal to 50 mm. We talk about the semi thickness. So semi thickness of the plate will be 25 mm. And we have to find the temperature at the location at a location 12.5 mm. Okay, so suppose this है ना, so we have to find this at 12.5 mm. So let's see, it is this distance is 12.5 mm. So we have to find the temperature at the location 12.5 mm away from the center line or mid plane within the plate. Okay, so for this we will find x by L first. So x by L is what? The semi thickness is 25 mm. So 25 minus this 12.5 and divided by L is what? L is the semi thickness, that is 25. So it is equal to 12.5 divided by 25. So it is equal to 1 by 2. It is equal to 0.5. Now we have this x by L, that is 0.5. And 1 upon Biot number, we have already calculated 1 upon Biot number. 1 upon Biot number is this 5.988. 5.988. This is 1 upon Biot number. Okay, now we will use the correction factor chart of correction factor. We will use the correction factor chart of plate. Let's see. this is the correction factor chart for the plate. So here you can see in the x-axis 1 upon Biot number is there, and these curves are expressed in terms of x by L. So in our case, this 1 upon Biot number is 5.988, and this x by L is 0.5. So on the basis of these two factors, we will locate a point on the correction factor chart. Okay, we will locate a point on the correction factor chart. Suppose we have located this as a point on the correction factor chart. Now we will take the projection. So we'll directly get the value of the correction factor from the chart. We are getting the value as 0.96. So that means this T minus TA divided by T naught minus TA is this 0.96. So let's go ahead. So we got T minus TA divided by T naught minus TA, it is equal to 0.96. Okay, so we can find T minus TA is 65 divided by T naught. So T naught value is 281 that we have calculated. Calculated 281 minus TA 65, it is equal to 0.96. So okay, so just solve this. So we will get one equation in terms of t. So we have one equation and one unknown. Just solve it so we can find the value of t. So calculated value of t is 272.36 degrees Celsius. So this is the answer. Okay, or the alternate way to solve the problem is we can find the okay, just a minute. Alternate way to solve the problem is we can find a temperature distribution from the Hassler chart for the temperature history of the center line or the mid plane temperature. So that is T naught minus TA divided by Ti minus Ta. And then we will find the correction factor for the plate from the correction factor chart of the plate. So we will get the correction factor for the plate as T minus Ta divided by T naught minus Ta. Now we will multiply this correction factor that we have determined from the correction factor chart of the plate with the temperature distribution that we have determined from the Hassler chart of the plate. Fine. So this T naught minus Ta will cancel out. So we'll get T minus Ta divided by Ti minus Ta. Okay, so we can find all this value. So definitely T minus T divided by Ti minus T, it was the value was 0.6. So we can say what is this? This will be 0.6. Okay, we got this value, and this value is nothing but this factor. This factor is 0.6 multiplied by this T minus Ta divided by T naught minus Ta. This is 0.96. So by 0.96. Okay, now Ta is known to us, it is 65. Ti is also known to us. The Ti value is Ti is 425. Okay, so we have all the values. We'll put all the values in this expression, and then we can directly find the value of value t. So here also we will get the value of t as 272.36 degrees Celsius. So in this way also we can find the temperature at the location other than center line or mid plane within the geometry. Here our geometry is plate. Okay, so this is the way to solve the problem without determining the center line or the mid plane temperature. So if it is not, if it is not asked to calculate center line or mid plane temperature in the problem, so you can directly find the temperature at the location other than mid plane or center line. Okay, by applying this approach. Okay, now let's go ahead. The problem number 7. Just read this. In question number 5, if the mean diameter of egg is 6 centimeter, thermal conductivity is 10 watt per meter degree Celsius, H value is given as 135. The remaining condition and properties are same. Find the time and compare the result. Just take 1 minute and just and then you just initiate this problem. Okay, so let's solve the problem. Let's solve problem 7. In the problem 7, this we will calculate Biot number, and Biot number is HLC by K. We will find LC first. So LC is volume per unit surface area. So this we are talking about the problem 5. So in the problem 5 you can see egg is there, so it is a sphere. Okay, so let's solve this. Just what we have to do here in this, in the question number 5, a mean diameter of egg is 6 centimeter, K is this, and H is this. The remaining condition and the properties are same, so we have to find the time and then we have to compare the result. Okay, for this, let's do this. So volume is 4 by 3 pi r cube divided by the surface area of the sphere is 4 pi r square. So 4 cancel, pi cancel, this r square cancel, so we got r by 3. So this we can say now the diameter is 6 centimeter. Now the radius is 3 centimeter, so 3 centimeter, that means 0.03 meters divided by 3, it is equal to 0.01. This is a characteristic dimension. Okay, now we'll calculate Biot number. So Biot number is HLC by K. So characteristic dimension we got as 0.01 meters. So H value, H what is given in the problem? H is given as 135. So 135 multiplied by LC value is 0.01 divided by K. The thermal conductivity value is given as, what is the value? The value is given as 10. Okay, 10. This value 10 watt per meter degree Celsius. 10. Just calculate this. So the calculated value of Biot number is 0.135, which is greater than 0.1. Okay, and lying in the range 0 to 100. So the Hassler's chart is applicable. Okay, so the Hassler chart is applicable. Okay, now rest of the procedure is absolutely same. Now what we will do next? It is the egg. Okay, so what we will do, first of all, let's see the our Hessler chart. So we'll use the Hessler chart for what? We'll use the Hessler chart for the sphere. Okay, and we'll calculate Fourier's number, and we'll calculate these. Okay, these lines are expressed in terms of 1 upon Biot number. So we have already calculated Biot number. We will calculate 1 upon Biot number. We will calculate Fourier's number. So let's do this. So we will calculate the 1 upon Biot number. Okay. Now we will calculate Fourier's number now. The Fourier's number, the formula for calculating Fourier's number is alpha tau by LC square. Okay, now with the help of Fourier's number and 1 upon Biot number. So this is Fourier's number on x-axis. The Fourier number is there, and these lines are explained in terms of 1 upon Biot number. So in term, okay, so we will locate a point on the graph on the basis of Fourier's number and 1 upon Biot number. So we'll locate a point on the graph itself. Okay. With the help of Fourier number and 1 upon Biot number, we will locate a point on the graph, and then we will directly take the projection. Okay, so we can get the value. We can read this value. Okay, particular projection. So in this way, we will find this factor T naught minus TA divided by Ti minus Ta. Okay, so this value we will directly get from this chart itself. Okay, so here fine. So it is a problem on egg. So that is a sphere. So we'll use the Hessler chart for the sphere. We'll calculate. We have calculated Fourier's number. And how can I calculate Fourier's number? Fourier's number is just a minute. What is Fourier's number? Fourier's number is a formula for calculating Fourier's number. We can calculate Fourier's number. We have already calculated 1 upon Biot number, and on the base of 1 upon Biot number and Fourier's number, we have located a point on the Hessler chart for the sphere, and then we'll take the projections. We can directly find the temperature distribution for the sphere directly with the Hessler chart of the sphere. Clear? Now, if I have to find the temperature at the location other than center line or mid plane, so we have to use this correction Hessler position correction factor chart for the temperature in sphere. For what? For this, we will find 1 upon Biot number that we have already determined, and these curves are expressed in terms of small r by capital R. We will calculate this factor also. We will locate a point on the graph, and then we'll take the horizontal projections. We can directly find the correction factor with the help of correction factor chart of the sphere. Okay, we can find this factor T minus T divided by T naught minus T. So okay, so we have already determined T naught minus Ta. So we'll put the value of T naught directly. The Ta value we know, T minus Ta divided by the T naught, that center line temperature. Okay, that we have already. Okay, that we can find. Okay, so okay, that value we will put here minus Ta, that is the ambient temperature. Fine. And remember this, we have already told you these curves are expressed in terms of small r by capital R in case of cylinder and sphere. We will directly get this value. We know T, Ta, T naught and Ta. Okay. So in this way we can find the solution, and then okay, so you just find the answers. And here in the problem, since the Biot number is greater than 0.1 for the problem number 7. So Hessler chart is applicable. So with the help of a Hessler chart, we will find the answers, and then we will compare our results with the problem number 5, which is the same problem, but here in the problem 5 the biot number was less than 0.1. So the lumped parameter analysis was applicable. Okay, so we'll compare our problem 7 result with the problem 5 results. Okay. So this problem is also solved. You just find the answers of this problem 7 and then you compare the result of problem 7 with the problem 5. Okay. The problem 7 biot number was greater than 0.1. So Hassler chart was applicable. And in the problem 5, the biot number was less than 0.1. So the lumped parameter analysis was applicable. Okay. We'll solve the problem and we'll compare the result of problem 7 with the problem 5. Okay, now the last problem of this problem set, that is problem 8. For question number 5, also find the instantaneous heat transfer rate 2.5 minute after start. And the second one is the total energy transferred from the egg during first 2.5 minutes. This we have to determine now. Okay, so very simple. All the parameters are given in the problem itself. Okay, so what is for what about problem 8? For the question number 5, that means all the so we have to solve this problem. Okay, for all the data given in the problem 5 itself, we have to find instantaneous heat transfer rate 2.5 minutes after start, and then we have to find the total energy transferred from egg during first 2.5 minutes. So let's solve problem 8. Problem 8. So problem 8. So for the problem 8, we have to find instantaneous heat transfer rate 2.5 minutes after start. So there is a straightforward formula given for this instantaneous heat flow rate. So we'll apply this instantaneous heat flow rate and we can find the solution. It is minus HAS times Ti minus Ta into exponential minus HAS divided by rho Vc okay minus HAS divided by rho Vc into tau. So this is the expression for calculating instantaneous heat flow rate. Instantaneous heat flow. So this expression we have already derived. We have already derived the relation for the instantaneous heat flow and the total energy or total heat flow. Okay, so this is the expression minus HAS times Ti minus Ta into exponential minus HAS divided by rho Vc into tau. Okay, so all the values are known to us. The value of H is given to us. We can calculate surface area, Ti initial temperature, Ta ambient temperature is known to us. We know the we know the value of density, specific heat. Okay, and we can find the value of characteristic length also. Okay, or that means volume per unit surface area, or we can directly put the value of surface area and volume in this expression, and the time factor for how much time. Okay, what is the time? What is the time for calculating instantaneous heat flow? So that value we'll put here and then we can find the answer. Clear? Now the second one is we have to find the total energy transferred from the egg during the first 2.5 minutes. Total energy transferred from egg during first 2.5 minutes. That means now we have to calculate total heat to energy. Let's see. Total heat flow rate, the expression is rho Vc times Ti minus Ta into exponential minus HAS divided by rho Vc multiplied by tau minus 1. Okay. So the expression for calculating total heat energy is rho Vc times Ti minus Ta into exponential minus HAS divided by rho Vc multiplied by tau in numerator minus 1. Okay, so this is the expression for calculating total heat energy. Okay, so all the values are known to us. We know the value of density. Okay, we can calculate volume. Specific heat is given. Value of initial temperature and ambient temperature is also given. The value of convective heat transfer coefficient H is given. LC we have. Okay, we can easily calculate LC value. Okay. So in this way, we have finished the problem set on the unsteady state heat transfer. We have solved all the 8 problems. Fine. And we have completed this problem set for this module 1.4, that is unsteady state heat transfer. So this completes module 1.4 unsteady state heat transfer, complete in all respect. And this completes the module 1 complete in all respect. Okay. Yes, can you hear me? Hello? Yes, anyone please respond? Yes, Hemal, can you hear me? Yes, Hemal, am I audible? Okay, so okay, so we have completed module 1 complete in all respect. Okay, so should we go ahead or we'll stop here? So okay, so today we will stop here, and in the next lecture we will discuss some concepts on the convection, and then we will solve some problems on the convection. That means we will solve the problem set of the convection in the next class. Fine. So okay, so we'll stop here. Okay, thank thank you for attending the lecture. Thanks for patient listening. Okay, so in the next lecture, we will discuss some remaining concept of the convection, and we will solve the problems on the convection. That means we will solve the problem set on the convection in the next lecture. So thank you so much. Thanks for patient listening. Bye everyone.